Вот так. Как есть. Ну, давайте я вам... So, okay, so let us start our lecture anyway. So, after the lecture, I shall send lecture notes. But, of course, yes, so that... So, I want to start with discriminant because it is a starting point of studying ramification locus, and but later we shall understand that well, discriminant it is of course when you are studying quadratic equation, it is precisely the discriminant of quadratic equation and as well of cubic equation. If you are speaking about just one polynomial of one variable. So in a sense it is important to define it, the object that generalizes it for the field, but then we shall understand that it comes from more fine object, yeah? And the reason is the following. So where does discriminant live, and where does different leaves? So you have the covering. So as usual, you have extension of the fields, yeah? And you have A is integrally closed in its fraction field, and you have B here that is integer closure of A in L, so also integer closure, and the degree of L over K is finite, yeah, so that what does if you think about solving equation 1, y is equal to f of x, yeah, so just you get the corresponding covering, so and you will have the ramification locus, so the points where, I mean, in general, if you solve such equation, then you have several roots, yeah? So the roots equal to, the number of roots is equal to the number of degrees. And when we are calculating this usual discriminant is what? It is just a product. So discriminant of f of x. So if f of x is a product of roots, yeah, so x minus alpha I. Yeah, so if so discriminant is the following. So it is of f is just the product of alpha I minus alpha j, and where I is less than j. Yeah, so the product of all pairs of roots and of their difference. And then you actually you are calculating you are calculating not precisely the discriminant, but the square of discriminant, but it doesn't much matter now. When you are starting the square of such a matrix, yeah, of such polynomial. So what does it say? So if two roots coincide, it vanishes. But notice that the roots are coincide upstairs. Yeah, so alpha I is equal to alpha j. So you have information about the coincidence of roots upstairs, and just a second. Да, привет, ну чё? Ага. Ага. Ага, супер. То есть ты посмотрел, оно заработало, да, трансляция? Да, здорово, спасибо большое, ладно. Извини, что дернул. Давай так. Yeah, so you have coincidence of roots, and but you are calculating it downstairs. So you are calculating it in terms of coefficients of f of x, and you get information that what information does you get that the corresponding point x where you have coincidence of roots. So morally, you are writing down, so you are not calculating. So when you are calculating discriminant, you are calculating discriminant, of course, not of precisely of f, but you are thinking of the polynomial f minus c, where c is the corresponding constant where you are calculating it. And then you, the phi bar is written as simply f of x equal to c, so c f of x minus c. And you are looking at the polynomial, just all its roots, and so these roots depend on c, yeah? So this of the constant. And of course, what does it says if your discriminant vanish? It says that alpha of c is equal to alpha j of c, but for some roots. And this is information of coincidence of roots downstairs. But morally, so there should be more precise information, because it can happen that roots over the point, they coincide in one point and coincide in the other point. And of course, just if we want to study more refined information, so we want to study, to keep track on these points. So I just keep track on ramification, upstairs. And yeah, so this means that a priori we can, so discriminant is easier to calculate in some sense, but I mean, for theoretical and some other practical purposes, we need the information that is ideal in terms of spectrum of B. Yes, so it should be ideal of B that those support, so those points that it defines, they correspond to ramification points. So that will be different. But let us now start discussing discriminant. So we have discussed just what we can do with the lattices. So the operator chi of A. So chi of A of module for finite. So if M was of finite length, so it was so we have considered associate prime decomposition of module, and so we have considered the filtration. Such that factors of filtration were prime ideals, and they were maximal ideals as well. And for this, we associate the product of ideals. Yeah? So just when you are thinking, when we have considered lattices, so also we have considered L gamma was called lattice in K, so in fraction field, if gamma, so gamma is a module, so gamma is a module inside K. Yeah, so we call it lattice if it is of maximal rank. Yeah, so that means that if gamma is finitely generated, is finitely A, and you take gamma, tensor it with K over A, and you get the whole, gamma is lattice in L, in the larger field. Yeah. So it's if gamma tensor L is tensor K is equal to L. Yeah, so the lattice can be also introduced for the vector space over the field. Yeah, so we can consider V more generally. We consider V as a vector space over K. Yeah, so we consider gamma subset of V as a lattice if gamma is finitely generated a module, and it gives you gamma tensor K, it gives you the whole L, the whole V. So now you see that if you have two lattices, so we have noticed that if we have two lattices, gamma and gamma 1 and gamma 2, yeah, so you can consider where they just you can so if you have two lattices, gamma 1 and gamma 2, yeah, so we can consider the following object. Yeah, so gamma 1 and gamma 2 can be put, so notice that you can take the basis such that gamma sits in AN, so by and it contains 1 over D. You can pick up a basis in gamma itself. Yeah? So I mean the problem is that the gamma in for modules over Z. Yeah, so the module of maximum. So the modules of maximal rank. So such that gamma tensor Q is equal to the whole space. Yeah, so it is free. Yeah, so module of the free module is free. So, but in general, it can happen that gamma has more generators than its rank, and this implies that you simply has a n as a subset here. But you can also write down all the elements or the basis of gamma in terms of basis of an and use denominators, and you see that it will be a subset of 1 over d an. So this implies that actually you can also do the following. So you can by writing down, for example, the basis of gamma 2 in the same way. So also you can do the following thing. You can take first of all, you can take the intersection of lattices, or you can take the smallest lattice that fits, that is both inside gamma 1 and gamma 2 by clearing up denominators, and you can also form the lattice gamma 1 plus gamma 2, and here it is, I mean, if you are speaking about gamma 1 and gamma 2, it is clear that it is finitely generated module. Yeah, so this is finitely generated, and here from this point of view you can express the elements of gamma 2, so elements of gamma 2 can be expressed via basis. In AN, and if you clear up, вы немного пропустили, потому что у нас трансляция чуть не накрылась. So you can express elements of gamma 2 via the elements in AN fixed basis. Can be expressed as a matrix Aij, J, and so Aij will be written as, of course, they can be written with denominators, so that Dij, and this will imply that so gamma 2, so this means that gamma 2, it will, you see that it will, I mean, so gamma 2 will contain when you want to express Ej, yes, so there will be a, so you have, so you are speaking about the basis, so you will have to express via inverse matrix, so just, so you have Aij, so let us, so here you do not, I mean, you do not care about denominators here in this form, yeah. So just a second. Что-то стереть не могу. Все стерли. So you are thinking about basis in. So EI is the basis in AN. So you are expressing it as EIJ. EJ, yeah? And you can take EIJ tilde to be an inverse matrix, yeah? So that coefficients of inverse matrix. So you see that gamma 1, etc., gamma n are expressed, I mean, Ej is are expressed as the matrix, so as the linear combinations of gamma I. So here I are expressed as here Aij gamma j tilde. And by, I mean gamma, so this gamma of the form Bij divided by some d, which is the maximal possible denominator, so the product of all denominators. So just you see that E1, En, so they sit in the lattice 1 over d gamma 2. So that means that gamma 2 contains the lattice d times an. Yeah? So so you see always that given any other, so even so when you're starting with any basis, so given any other lattice, you can see that it contains the lattice of d times a, and so you can pick up common d for gamma and gamma 2, so we can pick up this way for gamma 1 and gamma 2. So this implies that intersection is also a lattice. Yeah? So, which is, I mean, of course, it is finitely generated module, but it was not clear that it was of maximal rank.
Yes.
Yeah, so you have to dominate, but knowing that this can be dominated for, so you can dominate it for d times a n for some large d, this means that you can take, so this is still lattice, and gamma 1 plus gamma 2 is still lattice, and of course it contains in 1 over d a n, simply because the rank is maximal. I mean, you can have higher rank, and here you have understood that it is just writing down. So this is this d is keeping track on denominators of the first coefficients. So this means that you can consider, so in order to, so anyway, if you have common lattice that is equal to gamma 0, so we have considered chi of a of gamma 1 divided by gamma 2. So simply by considering chi of a of gamma 1 modulo gamma 0 divided by chi of a gamma 2 modulo gamma 0. So this was a recollection of what we have said. So also you can do the following. So if you have the vector space V, so you can have, so you can consider the map phi between vector spaces, between the same vector spaces. And if you have gamma here, so this is lattice. So if phi is non-degenerate, then I mean if kernel of phi is equal to 0, if it is isomorphism, that for phi of gamma is also the lattice. So anyway, so phi of gamma is finitely generated module. So this is finitely. So this really means that and you notice that so 5 gamma is lattice, so is of maximal rank if and only if this is so for 5 gamma is the maximal rank just because if and only if the kernel is equal to 0. Yeah. So otherwise, the idea is that you can take any basis in the kernel and use it a part of the basis for this an, and so just and so let me write it down. So 5 gamma is a lattice if and only if kernel of phi is equal to 0, since given basis e1, ek in kernel of phi, we can extend it to basis of v, and by clearing up denominators you can by picking up d, yeah, so you can assume that gamma contains d times e1 en, yeah, so d times this basis. Yeah, and this implies that I mean that phi of gamma will be of the smaller rank. Just because it will be a gamma modulo the part of the basis. So when you have so why I was recalling it, because you can form chi of A of gamma. Since we are in the same vector space, you can form gamma modulo 5 gamma. So you can calculate this thing, and if when you have just A is a unique factor principal ideal domain, so we can do the following. So as usual, we can diagonalize matrix. So we can write down 5 gamma. So gamma can be taken to the standard basis. So just AM. So here 5 gamma can be diagonalized. But here, of course, I do not mean that usual diagonalization of operator, because when you are speaking about linear operator in the same space, you are allowed only to make the change of basis of V. But I'm thinking about so far as the operator. So I'm taking different bases in image. So from V1 to V2, if you say that the spaces are different, you are allowed to, in order to put the operator in diagonal form, you are allowed to change basis of V and of V2. So this, in this case, you can diagonalize it over principal ideal domain. So it is D1, Dn, and but still you can calculate the determinant, and so this determinant of this operator is equal to chi of A gamma over 5 gamma. Maybe up to the sign, I mean up to -1 sign, so up to taking inverse. So this means just up to just in taking inverse. So this should be specified as the definition. So this suggests the following. So if you have some gamma and operator, so you can introduce. You can try to take determinant or try to take this thing, but notice that if so this suggests the following. So if you walk not over principal ideal domain, you can try to generalize it and in order to use this kind of observation. So how to make the definition independent of it. So if you have phi, the map from V into V, and you have gamma here and phi of gamma here. So the determinant is the relative thing. Yeah? So it is just the ideal that you should, of course, so during this change of matrices, so we should understand that we shouldn't multiply so when we are starting precisely principal ideal domains, we should understand that determinant should be, determinant of the change of basis should be 1, yes, so plus minus 1. So you are allowed to change the rows that will introduce plus minus 1 sign, but you are not, you are allowed to take the row and subtract another row with a coefficient, but you are not allowed to multiply the row by a coefficient. So anyway, so you notice that this change that we have done here, so they really are, I mean, of course, if you allow to change basis, the determinant will change, yeah, in the field. Yeah? But since you're working in the ring and you want to consider this, so since we are working in the ring and we are keeping track that the change of the basis here, so the change of basis result in multiplication by matrix with determinant plus minus 1, yeah? Which is important for using this formula and for proving this formula. Yeah? So this implies that я что-то писать стал, да? У меня стерлась просто страница. Yeah, so how we want to generalize it? Yeah, so if you yeah, so let me write it here. So this implies that the determinant of course needs bases. So of course need basis, common basis of V, of fixed basis of V, but you see that the matrix is changed by the product of elementary matrices, E1, etc., Ek, and so far phi is changed by, but E, K and E1 tilde, etc., EL tilde, and so determinant of this is equal to determinant of A, so that allows you to say that, and this will be equal to the product of D1, etc., D. So yeah, so this observation suggests now that you can do the following if you have arbitrary space. Yeah? So over, so at least if A is Dedekind ring, so you may do the following. So you may consider the lattice, and you can consider phi of gamma, and instead of considering this chi of phi of gamma over phi, you can consider the ideal. Yeah, and notice that for so this observation, so the previous part, it doesn't depend on the basis on the lattice gamma. All lattices are equivalent. Yeah, so under the transformations. But in general case, you may consider ideal generated by determinants of phi in the bases corresponding to all possible gammas. Yeah, so you can take gamma, but of course to write down determinant, you have to write down the basis. Yeah, so where gamma runs through E1 and En for all possible bases. So for all possible bases. And so you are generating ideal, and now so this is well-defined notion. It doesn't depend on the lattice gamma. So it runs over all bases. So the question is why it is the same notion as chi of gamma over gamma. So why?
So can you repeat what is that gamma of phi?
I mean, you are calculating determinant with respect to the basis.
Yes.
So you are taking gamma and taking the elements of gamma, and you are taking just I mean you are choosing sub-bases in I mean the gamma can have more generators than E1 En over A. So the problem is that you have to pick up all possible E1 En in V that can generate the lattice, and you in this basis E1 En you can write down what is determinant. I mean you know that it is phi is so this is a basis over K. Yeah, so this is not I mean it is of course basis of
So V is a vector space over K.
Yeah, V is a vector space over K, and you are considering integer lattices there. So you are taking the vectors and generated. I mean, you are allowed to take linear combinations with coefficients in A. So this is a very small space because K is not finitely generated over A, for example. It is just, I mean, from the viewpoint of, so if A is equal to Z, it is just lattice in the usual sense. But it can happen that, I mean, if you just take finitely generated module, then it can happen that it is not, it has larger rank than N. I mean, for example, you can take for arbitrary ring, yes, so because in Z all ideals are principal, but if you do not have this property, then ideals has more generators than one. Yeah? So that's why the thinking of from the viewpoint of the lattice, ideal is also the lattice because I mean also you can bound it from two sides by writing down D times A, where B is an arbitrary element of I.
So it's
principal
ideal.
No, I mean if you do not you can have not principal ideal, and but it contains principal ideal for trivial reasons. And so this means that any ideal it can be bounded from above and from below, and it behaves like A inside your field K. Yeah, so it's, and inside the vector space, and the lattice is I mean it is just something intermediate between A and A in the power N, and so я вообще не сделал. Это я понял. Yeah, so in general the lattice is something between A and D times A n, but you do not know that it is generated precisely by n elements.
Yes.
So that's the main problem. So, but if you want to write down the thing that tells you what is so for lattice you can consider chi of A of gamma over phi of gamma, and you want to calculate it via determinants. Yes, so for principal ideals we learned how to calculate it via determinants, And then you just want to do the following. So so in order to write down a determinant, the formula for determinant, you should pick up the basis in gamma. That is the basis of the vector space. So I propose you to do the following. So I propose you to pick up the all possible bases in gamma. So you take not bases. You take in gamma the collection of elements. Yeah. So let me just. So this ideal is generated by determinants of phi written in bases basis gamma 1, gamma n, where gamma 1, gamma n runs through the lattice generated by gamma 1, gamma a over a sits inside gamma, and so we run over all possible elements, possible collection. Notice that I could have said the following, so I could have said that we take all possible collections. I mean, or I could have said we can take all possible linear independent collections. That doesn't make change, because if you have linear dependent collection, your ideal is just 0. Yeah? Also, if you have, even if gamma is free, so it has basis gamma 1, gamma n, if you have if you can express the elements gamma 1, gamma n via the matrix times the other basis, where the matrix has coefficients in the ring A, then the determinant differ by determinant of this matrix. And this means that this determinant is just multiplied by the number from the viewpoint of ideal generated by all possible determinants, so that doesn't change anything. So the claim is that this is, so let me call determinant gamma of phi. Yeah? So the ideal generated by all possible collections of subvectors in gamma. And the claim is that this chi of gamma over phi of gamma is just this kind of determinant. And the proof is easier in our case, because so the formula, so this is so the determinant is not a number, it is ideal here. Yeah? So this implies that so you have to check the equality on ideals, and to check it, that you have to check the equality. When you are studying, so of course I claim that where A is Dedekind ring here. So to check the equality of pi 1 and 1, so the equality of ideals and k is equal to pi 1 m1, etc. by by k and k. Yeah, so in order to check this equalities, it is sufficient to localize it. Yeah, so it is. So to check the equality that ideal I is equal to some ideal j, where they are decomposed. Yeah, so it is sufficient. It is sufficient to check the equality after localizations. After localizations for all pi's. Yeah, so actually here you do not need to even to consider this pause. I mean that you can, so it is because I and j are submodules over the fraction field. Yeah, so you can compare actually. I mean, in order to, if you have a map of modules, you can check that the module is non-zero if and so you know that I mean if you you have more general situation usually in commutative algebra when you are taking about modules, so you have the map of modules. So you can take the kernel and co-kernel. Yes. So you can take kernel and kernel. So to check that surjectivity, you have to check that so kernel is 0, and to check injectivity, you have to check that kernel is 0. And for module, so you have to notice that for module M, we check it is equal to 0. So M is equal to 0 if and only if it is equal to 0 for all localizations. We know that where P runs through a spectrum of K. So spectrum of A. Yeah, so this means that when you're speaking about two ideals inside the fraction field, you also, I mean, you do not have a priori maps between them. Yeah? But you have the following, so you have, I mean, checking that I is equal to j in k. I mean, in the fraction field, you can form that it is sufficient to check that I equal to, so sufficient to check that I is equal to j and j is equal to I plus j. So that they are trivially contained in this module. So you are just taking so you have this map, yeah. So you know how to compare them. So if they are the subsets of the same thing, yeah. So so it is sufficient to check that the localizations are the same, and this means that. If you want to check that the localizations are the same, when you pass the localizations, you see that so you have to know that if you take localization with respect to any s, so this is exercise of that chi, so this chi is consistent with localization. phi of gamma s. And this is, the right hand side is consistent so this is just, this chi is just taking chi of gamma and localizing. Yeah, so that is the question, what happens after localization for the Dedekind range. Yeah, so if you have this sequence after localization, so this is, I guess this is in Dedekind range. Yeah? So in Dedekind case. Because so some localizations behave nicely with respect to maximal ideals. Some of them can kill more factors that you expect. But in Dedekind case, the localization is taken over maximal ideals, and they are maximal and minimal at the same time. So this is exercise. And if you are speaking about localization, so calculating determinant phi of gamma, so here it is easier, it is even easier to see that determinant of phi is equal to determinant of gamma s phi of s. I mean, here it is trivial. You just apply the same thing of checking all over the bases. And this implies that, notice that in our case, that chi of A in local, when A is local ring, is local one-dimensional ring, so ring, and the dimension of A is equal to 1. Yeah, so this is precisely discrete valuation ring. So we have, so A is principal ideal domain. So you have this equality, chi of gamma modulo of gamma is equal to determinant of gamma of phi. And this implies that you have this formula. Yeah, so this implies formula in general. So the next step is to saying. So now you see that we have come to discussing determinant, and then you have another interpretation of index. Yeah, so just. Yeah, so if you have the module, so I'm just rewriting this down. So if you have V and you have gamma here, so you have a map to given a basis. Given a basis gamma 1, etc. Given a collection of elements. So gamma 1, gamma n, collection of elements. Yeah, so you can map it to lambda n of v. Yeah, so you have also, so you can consider what you call lambda n of gamma, so the ideal generated, the subspace generated in subspace not subspace, a module, a module. So V is a vector space over K. Over K is equal to fraction field of A. Yeah, and you can consider gamma, and so gamma is a module, and you can consider lambda of gamma, so the thing that is generated by gamma, so you take the wedge product, and you take linear combinations of all such vectors over A. So that is precisely what I have said, and noticing that this is so so if it is highest exterior power, so this is just isomorphic to K. So this is so this thing sits inside K. So this is fractional ideal. It is finitely generated because gamma you can pick up these elements of so this is fractional ideal. Yeah, so the claim is that it is finitely generated, or you can think you can bound it. Yeah, so that maybe it is easier to prove that it is bounded, not finitely generated. Yeah, so that you can bound it from. I mean, you have a number that so here it contains gamma is contained in A n, and I mean, 1 over d times a n, and the d and contains d times a n, of course probably for different d's, but it is convenient to take the common one. Yeah, but so this implies that if you take this highest power, then what should I write here? It is contained where?
In 1 over t to the power n?
Yes.
Equals
Yeah.
lambda n.
I mean, there will be A, yeah, so that so there will be a standard basis, yeah, in A. And this A is a subset as just inside K given by standard basis A1, etc., which En. Yeah, so that you can bound this thing via d, and here as well. Yeah, so you are writing down d to the power n times a. So clearly this is fractional ideal. I mean, this thing tells you that it is fractional. So you prove that it is ideal because linear changing so changing the other basis result into the change. I mean, writing down other vectors from this given one, so allows you to write them down via integer coefficients, and I mean, of course, if you have additivity here, yeah, so you change one via the sum of the vectors, so that will be sum of the monomials. So that's why you are just having that the ideal won't be changed. Yeah, so this. Now we shall apply it to the space where you have bilinear form. So, and discriminant comes from this thing when we have a bilinear form. So, now we can come to discriminant. In order to define discriminant, we should consider bilinear form. So given bilinear form. Yeah, so you can also consider the the following. So you can consider the also bilinear. You can define bilinear. It defines bilinear form. On lambda kv, yeah, by writing down what. If you have the collection of vectors in V, so it is sufficient to define it on monomials. Yeah. So you have V1, etc. Vk, and W1, Wk. So you can define the bilinear form by the following. Just take determinant of the matrix where you take this bilinear form of Vi times Vj, Wj. Yeah? So notice that if you, so this is well-defined thing, well-defined bilinear form. Because if you interchange vectors here, yes, so it will, you have to understand that the answer will be just the same for monomials. So, well defined on monomials. So this means that changing vectors, just permuting vectors of V permutes rows, so V permutes rows and columns, so rows of matrix. So this result changed by -1 in monomial, and this result change -1 of determinant function, of the value of determinant function. And also you can, if you are defining it on monomials, you have to check that if you can express the monomial as a sum of two monomials, then you will have the same answer. Yeah? So you can express that the Vi in terms of Vi tilde plus Vi double tilde. Yeah. So that this results into calculating the determinant of B, where you are writing down instead of one row or one column, you write down the sum. So Vi Wj plus Vj Vi double tilde, and this, of course, if you change, if you sum up the row, the determinant is linear function with respect to the row. This is determinant of Vi Wj plus determinant of B of Vi double tilde Wg. So this is a well-defined notion. So just now we can speak about this bilinear forms can satisfy different properties. So for example, yeah, so you can form given gamma. So given and now you can think of the following. So now you have bilinear form. So given gamma inside V, yeah, so you can form determinant of B gamma. So you can calculate determinant between all possible for all possible bases. Yes, so that so you can pick up collection of bases gamma 1 gamma n, yeah, and also gamma 1 tilde gamma n tilde. So pairs of elements you can consider pairs of elements, and this yeah, so you can apply bilinear form to them. So these are subsets of gamma, and this is a subset in gamma. And you can take the determinant of bilinear forms gamma I, gamma j tilde, and generate an ideal by this values.
Yeah, there we consider that gamma 1 gamma n is the basis.
I mean, we do not consider gamma 1 gamma n as the basis, just arbitrary elements, because it can happen that if you are working not over Z, yes, so that these elements gammas can be not generated by n elements.
Yeah,
That is the problem. So the thing that we can avoid it via definitions. I mean, in algebraic number theory, usually people are just writing formulas for just writing down very specific formula that I mean that the discriminant is just some determinant. So you pick up basis, which is, so you take integer ring, you take I mean, of course, everything should be applied a posteriori to the following situation, that B is the ring of integers that contains A, it sits in L, yeah. And you are applying it to B equal to L, and B is equal to gamma. So, but if A is principal ideal domain, or when A is Z, so in particular when A is Z, yeah, so that this implies that B is Z to the power n, and this allows you to pick up bases in B and write down this formula explicitly. But if you want to introduce general concept of discriminant, yes, so you should consider the ideals where you run over all possible bases. It is more convenient, and you just do the following. You just prove that I mean, of course, you may say that you do not pick all possible elements, but only basic elements. Because and you see how it has changed. If the vector can be decomposed into the sum of two, then you just write down that your determinant will result into the sum of determinants. And this, if the lattice is, if the vector is A times the vector, then you multiply the element, and it is more or less clear that you can pick up all possible elements or only basic elements. But it is important at least to run over all linear independent elements. So just In particular, if you so let me write this down. So in particular, when gamma is free, so when gamma is isomorphic to an, yes, so you can pick only one basis. Yeah? You can pick basis. And write down determinant. So write this down for one pair of vectors. And write determinant of B, EI, EG. Of determinant of the gram matrix of the basis. Yeah? So let us recall what is, now I want to come gradually to different, and it will be clear. So I'm just restating all these things in order to understand that the notion of different is natural. So now let me recall that what can you do? So you can, if you have just inside V, so you can think of, so if V is non-degenerate, the bilinear form is non-degenerate. So this allows, so V identifies with V dual, and yes, so simply by taking so you should say what is linear function associated to V. You associate the linear function L of V that is calculated on W via taking bilinear form by V and W. So of course, when V is not symmetric, yes, so that you have two ways to do it. Yeah, but you have right dual, or so identification for right dual and for left dual. And if you're taking, so this allows to speak of if gamma is a free lattice. So when gamma is a free lattice E1, En. А где? Non-degenerate. Не вырожденный. Bilinear form. Yeah, so if you have now three bases, so if you have a basis, you can pick up dual bases. Yeah, so you can pick up dual bases. And this is called gamma dual lattice, with the property that just EI is so EI psi I, so the bilinear form of EI psi I, psi G is just Kronecker delta symbol.
Yeah, and you then assume that gamma is generated by n elements, yeah?
Yes, I am just writing down this. Yeah. So this you can introduce the matrix of matrix of changing of coordinates. Of EI is written as AIJ XII, XIJ. So this is just matrix D that maps. So yeah, so it maps Xi1 psi n to E1 En. Yeah? Ну, я сейчас его более общее как бы определение скажу, ну, что такое гамма двойственная. Мы легко поймем, это просто, ну, как бы для начала мы стартуем, ну, от самого простого понятия. Yeah, so you can speak what is...
Yeah, so how we change it, so how we...
Ну,
why
просто...
EI equal to psi j, it's basis in...
Yeah, so this is, I mean the one En should be basis in V.
Yes.
Yes, and this is basis in V as well.
In the...
In V, I mean, this is...
yeah, of course,
yes.
Yeah.
Here, you identify them.
Yeah.
So to... So you can pick up and notice that actually this B, so the matrix that maps here, yeah. So it is in order to so let us calculate Gram matrix of E. So here I and EJ. Yeah, so it is equal to B of. So let us calculate it EI as if it is written in terms of basis of psi I. This is EI, the sum of A J K, psi K. And this is equal to, so of course now you have to use Kronecker delta symbol, and it is just I J I of B, so B E1 B E I psi I, so that is equal to 1. Yeah? So this is precisely AJI matrix. So you see that this operator that maps psi1 psi-n to 1 En, it is just it is given by the matrix, which is Gram matrix. So if you want to relate with the previous ones, then you see that you can consider determinant of gamma with respect to this operator B, and it is equal to the operator given by Gram matrix. So claim that we have seen from the previous one. And then you can do the following. So if you have more generally, you can think of taking the, so instead of the ideals, you can pick up, so instead of taking gamma and taking, so you can pick up so more generally, you can pick up in gamma the collection of elements E1, En, and in gamma dual you can pick up. Yeah. So what is gamma dual, by the way? So the gamma dual. Now we can define gamma dual. It is equal to what? So it is the set of values. Yeah, so it is the set of elements in V. Yeah? So such that B W, so it is a bilinear form with the value in K, but you have a subset A there. So want that this value lives in the sum. And this, so you can define, instead of writing down this gram matrix, you can think of the bases of E1, En, and the dual basis is Xi1, Xi(n). So Xi(i) is dual basis. To EI. And if you take the basis, notice that if you take the basis and take any other linear change with respect to A, this doesn't change the ideal generated by this bilinear form. So this means that what you can write down either collection. So what you are calculating is just you can take the values of you can think of this as you can write down this as we define discriminant. Define discriminant via the following observation. So this is either a determinant of phi. Yeah, so you can consider B as a map from V to V. Yeah, so the corresponding phi. Yeah, so you can define it like saying that you are taking the determinant of B, EI, EJ over all possible bases. So where E1, etc., En is the subset of the vectors. Yeah, so you can generate the ideal by it. Yeah, so you can write down B as an operator between V and V dual. So B is gives operator. And this allows to operator precisely with the matrix given by gram matrix. Yeah, so that is determinant of phi of gamma, and this will be so where gives operator phi given by the matrix, so B, E, I, J, that maps a basis to the dual basis. And this also, so notice, so this will be equal to our value chi of two lattices, gamma and gamma tilde. So gamma and gamma star. Notice that if you take two vectors, so that E1 and you start with two different vectors with the property that their value is equal to 1. I mean that bilinear form gives you 1. Yeah, so that you get that you get the following. So you can extend them to the basic vector. to the basis. Yeah? So that's why the precisely the matrix that we are talking about maps the basis gamma 1, gamma n to xi 1, xi n to e1, en, and you can extend. So I claim that any vector of gamma star can be obtained as the map of this form. I mean that. So we have discussed only the maps about the basis. So we have taken the basis. It allows to take to take the dual basis. Yeah. So that we have started with the following observation. We have taken the basis e1, en, and constructed, associated simply the dual basis. Yeah, so if you have, you start with two vectors, just v and double u, so such that bilinear form is equal to b of v double is equal to 1. Yeah, so you can extend them to the basis. So we can extend it to the basis. To bases. So via e1, en. So that's why the ideals that we are talking n minus 1 and 2, we can think of it the map to w and xi 1, xi better to say xi 2, xi n. And this tells you that the things that we have considered generated by all possible bases are just so they are the same. Yeah, so that this I mean these notions that we have defined. So we have defined this via сейчас давайте глянем. Ага. Вполне возможно. Тут не дописано, тут нам для любого W с гамма написано. Это...
Нет, у нас гамма со звездочкой это же оператор, да?
Нет, гамма со звездочкой это решетка. Извините, я забыл, что вот это условие для любого W с гамма.
Сейчас как бы есть гамма и решетка V.
Да, а это двойственное.
Там же.
То есть как бы гамма она, грубо говоря, если бы, ну, то есть вот это вот определение, оно не зависит от, здесь мы как бы свободное брали решетки, да, ну, то есть как бы порожденные ровно n элементами. Тогда, если у вас есть решетка, то двойственное разумно назвать это то, что у вас есть базис, вы берете двойственный базис, вот это то, что порождает двойственную решетку. Но с другой стороны, ну как бы, это плохое определение, оно от базиса зависит. Да? Поэтому если вы хотите, чтобы оно не зависело от базиса, надо тогда как-то менять вот этот базис, смотреть, как меняется вот этот базис двойственной решетки. Поэтому это определение не очень хорошее, а более правильное и простое. Просто я начал с тех формул, которые, ну, которые нам нужны, то есть как бы промотивировал. Но правильное понятие, конечно, вот такое, да, что вы берете просто те вектора, которые спариваются с векторами с гаммы, и дают элемент SP. Вот. Ну и теперь как бы можно когда у вас есть уже двойственная решетка, то вам удобно написать гамма и гамма со звездочкой, да, и тогда вы можете написать вот этот оператор, вот кай, но кси, хи, точнее. Вот, но как бы еще у вас есть разное представление вот этого оператора. Можно думать о нем, что у вас есть, ну, определитель фи, где вы фи берете, ну, вот с помощью относительно разных базисов гамма порождаете вот этим определителем. Можете также брать вот ту матрицу, фиксированную матрицу гамма, и смотреть на вот ее значения в Е и Т, Еж, Т, где у нас пробегают разные значения базиса. И вот как бы то, что мы получаем, это как раз где вот это вектора подрешетки, да, ну, это как раз то, что нужно, да? То есть вот просто потому что вот это вот буквально матрица вот этого оператора. У нас есть еще более общее определение, когда вы разрешаете варьировать элементы здесь и вот здесь, но ничего нового вы не получаете из-за этого тоже. Ну, в смысле, можно брать ЕИ, Т, а тут ЕЖ, Т с волной, тоже элементы из гамма.
Ну да.
Но вот в этом меньше элементов. Ну, то есть, как бы, что вот это, оно же равно определителю, то идеалу, порожденному определителем ЕИ, Т, ЕЖ, Т с волной.
Ну просто ж мы не... Сейчас мы будем...
Ну, можно брать по всем элементам из гамма, ну, в смысле, базисом из гамма. А можно брать по базису, по паре базисов.
Ну да.
В гамма.
Почему вообще разница какая-то?
Ну,
почему там?
ну, потому что вы вот этот вот базис можете, он не может не выражаться через этот базис.
Ну да, это правда.
Вот из-за этого вы как бы хотите, ну, что иметь определение через буквально вот этот, ну, как бы оператор и не, ну, как бы независимое определение, что они связаны. Ну вот, и как бы, ну а смысл, что можно вот работать с базисом, вместо базиса в двойственной решетке, потому что тот оператор, который E1 должен перевести в Кси1, он может быть, ну просто, как бы, да, если у вас есть элемент из двойственной решетки, то он может быть получен вот таким преобразованием. Поэтому мы все элементы из двойственной решетки покроем. То есть, ну вот, so now we can pass to different. So now we have is algebraic now. So different. So now you start with the following bilinear form. So just if you, so for bilinear form B, we take trace form that maps from L times L to K, and to K. And when A is integrally closed, when A is integrally closed, we have B times, we have the following. So trace can be viewed as the map from b times b, and the target is a. Yeah, so the trace the linear function. Yeah, so takes values in. So this. Now the discriminant actually is, gives you a fractional ideal, but when you are considering just so note that discriminant is fractional ideal, so discriminant of so you can pick up a discriminant of b over a. Yeah? So thinking of b as a lattice over a. Yeah? So b sits inside a n and 1 over b inside a n and sits inside a n, and so you can pick up discriminant that maps to.
And discriminant we find as the chi a of gamma over gamma.
Discriminant, yes, it is defined as as determinant of gamma star over gamma. So up to the sign. Yeah. So this that is so you have so discriminant is the element of fractional ideals. So it is a fractional ideal. And notice that so if A is equal to Z, you just so you have A is equal to Z. So it is just integer number. Yes, so discriminant is integer number. So you see that so we define as before. Yeah, so you can define the ring. B dual, which is a dual lattice. So B dual, it is the ring of. So the set of elements B, so such that trace of B times B1 is sits inside A for any B1 inside B. So maybe just let me say that. So it's an element X such that trace X B sits for any B inside B. And this, so this suggests that so notice that here it is precisely the definition of the dual lattice.
Isn't it true just for any X?
Нет, no, is K. So this is the definition of dual lattice. Dual lattice.
Может из L? Может из L? Ну, то есть у нас же
Да, да. Извините. Yeah, so this is a definition of dual lattice for V equal to L, and yeah, so B equal to gamma. Yeah. Ой, что-то я перепутал местами. Yeah, and notice that as before, notice that yeah. So what we haven't said before. So I mean, I consider that to be evident, but maybe it is worth commenting, of course. Yeah. So of course, when you're thinking about definition of dual lattice, it is a module. Yeah.
Yeah.
So notice that note that gamma star is a module. First of all, yeah. So also just because you can multiply by AV, yeah, so W, it is just so you have multiplicativity. Yeah? So also it is submodule, so you have, yeah, so here it is important that A is the same, so you as coefficient. Yeah, ring. So of course it is a submodule, that's not because you can, the sum of such conditions is also, because you fix W, so you can take the sum, and also, yeah, so what is less clear here that it is finitely generated.
Mm-hmm.
Yeah, but this is again because you can clear up denominators. Yeah, so you can bound. You can put gamma in actually you can write explicitly just how you can, if you can put yeah. So notice that. So here it is so the remark, so that so let me write this as additional remark. So how we prove that gamma star is finitely generated? So why gamma star is finitely generated? So actually, for very simple observation, so indeed, if so observation one, that if you have two lattices, so if you have gamma 1 and gamma 2, the duality reverses the inclusion.
Mm-hmm.
Simply, this is just this is the reverse of the condition. Yeah. So in order to prove that gamma is finitely generated, you have to bound gamma by the lattice where a priori you know that it is finitely generated.
Mm-hmm.
So how you can do it? So you can pick a gamma and put it as before inside 1 over dAn, and put it this inside the dAn. If you take dual, the dual of this one, so the dual of this lattice, yeah, is what? It is at least it sits in 1 over d to the n. So this is gamma 1 and this is gamma 2. Yeah? So that means that gamma star is bounded by gamma 2 star and gamma 1 star, and this is bounded by 1 over d in the power n a n.
Yes, so we work in only Nazarian case, yeah?
Yeah.
Mhm.
So this automatically tells you that gamma star is finitely generated, and this is actually this is precisely what we did in order to prove. I mean, this is just recollection of the proof that B sits between 1 over B, and because we just you see that we precisely proved that why B was finitely generated, because you have we have used precisely the following observation. Yes, so let me recall it that we have we wanted to prove that B. Yes, so we wanted to prove that B is was finitely generated. So to prove that B is finitely generated, what would pick? We picked up the dual lattice. So we picked B star, and notice that B star trivially contains A. That was important observation. So note that B star contained B. It contained B.
Yes.
Yeah, simply because trace of B1 and B2 sits in A. Trace of B1 and B2 sits as a subset of A. And we proved that B is to prove that B is finitely generated. We just could do the following. We have to pick up. We picked up B star. Yes, so it contains B, and the B contains the basis. Yeah, so we have picked up basis, so a to the power n over d, just because that any integer, any omega that belongs to L, yeah, so any element from L can be made integer, by multiplying by taking d omega. Yeah, so we have picked up basis omega 1, omega n, arbitrary basis of b of L over k over a. And we made it basis. We made it basis inside B. So by putting d omega 1 as d omega n, we put it inside B. And our proof looks like the following. So you have to take this thing, and when you do duality, so via duality, taking dual, so it reverses. B sits inside B star, and it sits in the 1 over D an dual, which is isomorphic to an. So that's why we have bounded B star via this trick, because you have some lattice. So it is. I mean you. So conceptually, so this bounds the B. Yeah? So this bounds B. This is actually this explains the conceptual part of the trick that we have done. So let me do 5 minutes break. Okay. We can. I shall come up with definition of different. Yeah. So what benefit do we see? So first of all, so we see that. So B star, B star is not. So what is good about this module B star and what is bad? So what we know. So first of all, we know that B star is a B module. B module. So for a very simple reason again. So we have a multiplicativity of. So you have x. So x sits in B star, yeah, so you take B1 that sits in B and x times B1, yeah, so it is times B, clearly sits inside A, yeah, so because already you just open brackets and you see that, so here it is the same as x B1 times B. Sits in it. So the same condition that x satisfies. And this tells you that B is B module and B is contained in B star submodule. Yeah, so you, in particular, B is a fractional ideal. Sorry. So, yeah, so what we also know that B star is finitely generated, yeah, because dual of, I mean, just because we have bounded it, yeah?
Mhm.
So, just B star was bounded. So, B that sits in B star was bounded by 1 over d to the an, and this really tells us that B star is finitely generated, generated A module, and in particular B module. And B and finitely generated B module. So this really means that B star is fractional ideal. Yeah. So in our case, so it is a subset of L. So B star is fractional ideal. So we can invert it. And the benefit is if you have I and J, so why we want to invert it? Just because if you have I and J, so this, when you invert ideals, you have opposite inclusions. And this implies that since you have opposite inclusions, you have so B star inverse sits inside B inverse, which is B. Yeah? Yeah, so for that it can break. Yeah? So this is for that it can break. And this implies that so this thing becomes ideal. So this is ideal that we call different. And now we can, so our long discussion was in order to understand how this B is related with discriminant. So notice that we had formula. Yeah, so actually this, so different lives upstairs, it is ideal upstairs, and the discriminant lives downstairs, it is ideal in A, yeah, so this is fractional ideal in P. So the claim is that norm of different is just discriminant. So we have operation of norm of AB, so claim that norm of different is in B over A, so it is discriminant. And now it will be clear why we want to consider the things, so why I was, it was important for me to write down discriminant in terms of chi. Yes, so notice that if P is equal to gamma, so we denoted discriminant as discriminant was of B over A was equal to chi. So let me, so at least in my lectures, I have, at least I think I tried to keep it right on. Yeah, so what? No, maybe it was to the sign. Yeah, so this is this was chi of A, so it is important that it is over A of B star over B. And notice, yeah, so that notice that we had the following commutative diagram, yeah, so that from B modules you have mapped to the ideals over B, and here you have restriction map to A modules.
It's chi A, B star over B. Usually we have gamma over gamma star.
Да, ну может это я ошибся, я не помню. Ну, то есть, да, да, ну с точностью до знака, и вот, so this is up to the sign, and I don't, I mean, it is one can choose it, so the definition, so that's why. So I'm afraid I didn't keep track on it. So if you notice that we have the following, so we have two maps between, so this is fractional ideals, fractional ideals in B, so this is fractional ideals in A. Yeah, so this is just so here the upper arrow is chi B, so this is chi A, and so here is a restriction map, and here is a norm map. And now it will be clear, so notice that if you have chi B with respect to, I mean, chi B is taken to be as relative. So if you are thinking about chi B over B star, it is just it is up to the sign equal to the inverse B over the corresponding ideal. And this is equal precisely, I mean, as the fractional ideal, it is equal to B star of minus 1. Yes, so the definition should be done as that in such a way that the value of this thing is just B star inverse. I mean, I do not keep track, so how we did our definition in order to have B modular ideal is just its ideal, so notice that chi of B modular I is just by definition is the ideal. Up to the same. Ну, потому что у нас в К-группе есть вот такая точная последовательность. К от бета.
Сейчас, ну, Кай мы же там определяли через эти решетки и все такое.
Нет, Кай, он как бы был через модули конечной длины.
Да. Ну да.
Ну, то есть мы фильтровали и определяли в К-группе.
Ну а Б свободный, да?
Да. Из-за того, что Б свободный, то он отправляется в ноль, и у вас как бы вот, по крайней мере, ну как бы с точностью до, ну там плюс-минус, ну то есть как бы это и в минус первый, да, с точки зрения определения. Поэтому как бы, so in particular you see that if you apply this commutative diagram, you will see that norm of, so on one hand, chi of A is just a norm of, so B star over B is just the norm of chi of B. And by this equality, it is just a norm of B to the power A of B star of inverse. So that's why we have this formula for different. It is more or less a tautology from the viewpoint of a formula on K-groups. So that was the reason of this very long discussion, because actually, so so there are two steps. So first of all, to understand that this difference is the norm, and it is easier to understand that via this universal property. Yeah, and this is just yeah. So this is restriction. So here, of course, I should have written restriction. Yeah? So. Restriction of B star of B as a module. So that is one part, and the other part is just the other part is just so discriminant is usually defined via this determinants of the trace map, of ground matrix. So that's why it is we needed to just associate that definitions, and that's what we did. So properties of different. Let me see a few properties of different, and I will finish for today. So suppose you have a fractional ideal in A. And the B is fractional ideal in B. So then you had equivalent properties. So just the following conditions are equivalent. So the trace, so the question is how to check the trace of B lies in A without without calculating trace map. So first the condition that this trace lies in A, and the second is that instead of calculating trace, you can simply use a different, that B differs from A just by different. So, of course, yeah, so you consider A as, you may consider A as ideal, so it works like ideal that generates, so this product is the corresponding ideal. Yeah, so the proof is just the following, that condition condition that trace of yeah, so here you have to notice that yeah, so let us just let us do the following. So proof. So proof. Yeah. So a trace of B sits inside A. So notice that you can swap. So since we're working with fractional ideals, this implies that A inverse trace. So you can invert the ideal. So A inverse trace sits inside A. And if you are thinking about elements of K, you can move them inside. So from A linearity of trace this is equivalent. Yeah, this is if and only if that trace A inverse B sits inside A. And notice that this is ideal in B. Yeah? So this is ideal in B. So you have to. So we have to reformulate this condition so we claim that this is if and only if the ideal A inverse B. Yeah, so it should, so of course this thing should live inside B star.
So what is A inverse B? It's what it, so we multiply the fraction ideal that sits in K
Yes.
with an ideal that sits in L and in B and in L. How we multiply them?
I mean pairwise. I mean everything sits in L.
Yes, we can multiply, but why is an ideal?
it is ideal. You take pairwise. You take ideal generated by the pairs.
Okay.
Yeah. So notice that. Sorry. It's not. No. It's there is misprint. I didn't want to say this, so it's not ideal in B. This is fractional ideal with respect to B. So ideal with respect to B. But notice that, so of course, if this holds, so you can say that, so you can say in this direction. But notice, this is precisely, but for ideal, for ideal I, fractional ideal, with respect to B, so if already you have ideal, so the condition trace of I sits in A, whenever, so and trace of B I sits in A are equivalent because I is ideal.
Yes.
So are equivalent.
Mm.
So this implies that simply, that arrow is two sides. And so this implies that already we have also arrow in this direction. Yeah, so whenever you have this already, you see that now you just rewrite it to get that this implies that B sits, if you invert it, so this is different in the, this implies that B sits inside A times different of B away. Of course, so here, this thing doesn't keep track, it is not, the reason we're discussing, so the proposition that we're discussing here, so it is characterizations of ideals. Yes, so if, without saying that your set is ideal, so of course this taking that traces inside A is not equivalent that B times I is inside A. But when we're speaking about fractional ideals for B, then it is clearly in both directions, and you have so out of so non-trivial part is how to derive out of this the condition for trace.
Why is from A minus 1B lies in B star?
So A moves here by multiplying by A, and B star is the inverse of the difference. Just by definition. This is so this is and we shall use this characterization in order to next time in order to prove how different is changed under extensions, and then this will allow to rewrite different for different types of extensions for ramified and unramified, and that will explain. So we shall relate the different precisely with this ramification indices that we have introduced before. Yeah, so thank you. So, next, in the evening I shall give you problems for exams. And I plan to do the following, so I plan to have oral exam in our usual time, but I give you the list of problems, and I shall check them during the exams. So since just people stopped attending my lectures somehow, so I want to have, so usually I was asking my questions about solutions online, so here I want to be more strict and just to have some kind of discussion. So be prepared that which I'm not going to ask you theoretical questions like prove directly unit theorem, but of course I can ask, so can you formulate the Minkowski lemma? So the crucial step in the proof. Yeah? So without, of course, details, but for example, I can ask what is the definition of discriminant. Or just discuss the proof of the formula. So like this. So of course, I want to be asking very deep questions that just have the length as the lecture. Similar to the length of the lecture. It is just some short theoretical questions in order to check your understanding, that you know the notions that you are talking about.
Когда будет экзамен, получается?